IEEE ECE 201 Electrical Circuits 1. In the previous lectures, we have studied how to solve individual networks having series and parallel configurations. In this lecture, we will study how to solve circuits which has combined series and parallel configurations. We will also study how to determine the equivalent resistance of such circuits. And at last, we will cover the topic of source conversion. An electric circuit or network can be classified having two types of configuration. Number 1, a series parallel configuration. Number 2, a complex configuration. A series parallel configuration is one which is formed by a combination of series and parallel elements. Whereas a complex configuration is one in which none of the elements are connected either in series or in parallel. If you look at the example given over here, R3 and R4 are connected in series because they have one common node. Then this entire branch from here to here is parallel to R2. Then this portion of the network is in series with R1. Hence, this network is an example of series parallel configuration because all the elements are connected to each other either in series or in parallel connection. Example 1. For the given network, which is this one, we have to determine the currents I4, Is and the voltage V2. I4 is the current flowing through resistor R4. Is is the source current that is coming out of the source. And voltage V2 is the voltage across this point. If we look carefully, there are no two resistors in this network which are directly connected in series configuration. And the only parallel combination is resistors R2 and R3. Therefore, if we determine the combined resistance of these two resistors, then it will be representing the parallel configuration of R2 and R3 as R prime equals 1.8 kilo ohm. Now, let us redraw this network with the equivalent resistance of the parallel combination of R2 and R3. Hence, the voltage source will remain as it is. R1 will be drawn as it was in the previous network. R4 will also remain as it is. The only change will be over here in this portion of the network where R2 and R3, the parallel combination, will now be represented by the equivalent resistance R prime, which is equals to 1.8 kilo ohm. Now, we know that R2 and R3 are connected in parallel, and in parallel combination, the same voltage drop will be across both the elements. Hence, now V2 will be the voltage drop across R prime. One thing which you must remember while redrawing the network is that you cannot change the polarity of the potential drop across the resistors or the polarity across the source. You can also not change the direction of the given currents. Remember, we are redrawing the network to simplify it. We cannot change the design of the network. Now, since we know R prime, R1 and R4, this simplified network can be used to determine Is, I4 and V2. If you observe carefully, now R1 and R prime are in series and this branch is in parallel connection with R4. So, we can easily determine I4 using Ohm's law. Since this branch and this branch are connected in parallel, Therefore, they will have the same voltage. Over here, this branch has a voltage of E, which is equals to 12 volt. Then this branch must also have a potential drop of 12 volts, as well as this branch must also have a potential drop of 12 volt. Hence, I4 is determined using Ohm's law with the formula I4 equals V4 by R4, which is equal 12 volt by 8.2 kilo ohm, which is equal 1.46 milliampere. Now, we know that the total voltage across each of this branch is 12 volt. Therefore, we can easily determine the potential drop across this point using the voltage divider rule. So, V2 equals 1.8 divided by 1.8 plus 6.8 kilo ohm times 12, which is equals to 2.51 volt. Now, we can determine the current flowing through this branch, because as we can see that over here there is a node. So if we apply KCL over here, then IS, the source current, must be equal to the current flowing through this branch and the current flowing through this branch. So we can determine the current flowing through this branch using the formula I1 equals E divided by R1 plus R prime, which is equals to 1.4 milliampere. Then we can easily determine IS using the formula I1 plus I4 equals 1.4 plus 1.46 milliampere, which is equals to 2.86 milliampere. Now, this is one of the way in which you can determine IS, V2 and I4. You can also use other techniques to determine these variables. Example 2. For the network given over here, we need to determine the voltages V1 and V2 and the current I. Now, before moving on with the calculations, it will be easier for us to understand this network if we redraw it. So, in order to redraw this network, I'll consider one of the nodes as a reference node or a reference point. Over here, I'm taking node A as the reference node. While redrawing the network, I'm representing node A as a straight wire. Now, if we look at here, node A has R3 and R2 connected in series, and then the other terminal of R2 is connected to the ground. So, if this is node A has R3 and R2 connected in series, and the other terminal of R2 is connected to the ground. Then we have another branch at node A which has only one resistor R4. Since over here the other end of R4 has no connections, therefore you have to assume that this terminal is connected to the ground. This is node A. From here we will draw R4 and the open terminal of R4 is connected to the ground. Over here to the right there is another branch which says E1 equals to minus 6 volt. This means that on this side of A there is a voltage source connected, and the minus 6 volt basically denotes that the negative terminal of the voltage source is connected to A. Since the positive side or the positive terminal has no connection as shown over here, thus we will assume that the positive connection or the positive terminal is connected to the ground. There is only one remaining branch over here, which is this one. So, if we start from here, from node A, we have R1 at first and then E2 plus 18 volt, which means that the positive terminal of the voltage source E2 is connected to R1. And since the connection of the negative terminal